Our next speaker is Dominika Przewlocka-Rus, and the topic of the talk is Power of Two Quantization for Low Bitwidth and Hardware-Compliant Neural Networks, and the speaker is from Meta Reality Lab.
Hello everyone, I hope you can hear me. So actually Dominika is not here today. She worked with us from Poland because of this COVID situation, and also she couldn't join us here today. So I'm Syed, I'll be presenting on behalf of her. So today I'll talk about this nonlinear quantization effort. So the previous speaker already talked a lot about low precision quantization. So that I believe that will help us to understand this a bit more. Okay. So we all know the main key problems of tinyML hardware implementation. Memory constraint and compute constraint. On the memory side, we are mostly limited by the form factor, and the memory nowadays consumes most of the area of the hardware accelerated device. And we also don't want to use external off-chip memory, for example DRAM, because it requires orders of magnitude high power and latency. And the quantization is one of the key options to reduce this memory footprint and corresponding power consumption. Okay, on the compute side, again we are dependent on mostly battery power for edge IoT devices, and for compute we are focusing on this image based inputs which require convolutional neural networks, and those mostly depend on multiplication operations, which are the most power hungry component in hardware accelerators for neural networks. So reducing bit precision definitely will help, and it can lead to exponential power reduction, and even better approach can be completely replacing this multiplication operation with something simpler. So based on that, we tried to explore first standard quantization methods, and we found that for 8 bits, the accuracy loss is almost negligible. So we took that as a standard for our comparisons. But if we try to go below 8 bits, we see some accuracy degradation, and as you have seen before, like 4 bits or below, the accuracy loss is significant. So because of that, we considered some different quantization techniques. Like the standard quantization technique now is linear quantization or uniform quantization, where each levels in the weight distribution will have equal distance. On the contrary, we explored logarithmic quantization, where we have unequal distance between different levels. So here maybe I can show you some examples. So this left figure, this is a floating point weight distribution of a particular layer in a convolutional neural network, and you can see it's almost continuous curve with a Gaussian distribution. And if we go down, apply linear or uniform quantization, the distribution will look something like this with a very low precision, maybe 3 to 4 bits. So here something we can note that in the floating point distribution, most of the information was around this 0, and there is a high density. But when we apply linear quantization, a lot of the information is lost near 0. And that actually is one of the main reasons of this accuracy degradation when we go to low precision. Then how we can save this information? The idea was if we have more levels near 0 and reduce the number of levels as we go far from 0, that should help. And based on that, we tried to apply logarithmic quantization, and this is an example of that application. And like previously, there are quite a few works that also explored this kind of nonlinear quantization. So on top of this standard logarithmic quantization, we impose another like constraint, because we are not only worried about accuracy, we also want to get maximum benefits from the hardware as well. So we also included this constraint of log base 2 quantization. That means we will only use power of 2 weights, like 2 to the power x, and x can be positive and negative. This will help us to get rid of the multiplication operation and use only bit shift operations for the convolution cases. So the key differences between standard linear quantization and nonlinear quantization are like this. One is, I already mentioned, that the difference between the weight levels are equal in linear quantization, but in nonlinear quantization, you can see the levels around 0 are very dense compared to the levels far from 0. So the like distance will be different, and this brings a new challenge in the training, because usually we apply one learning rate that is equal for each of the weight updates. But if we use that same technique, this will not help to regain the like accuracy loss because of quantization. Here I can explain the difference better. So assume that we run a retraining after doing the quantization to compensate for the quantization error, and if my learning rate is fixed and this value needs to go on the left, like being decreased, it will have some like learning rate based decrease. But for going forward, or if we want to increase it, if we use the same learning rate, it will not be able to jump this far. So we need to apply different learning rates based on the direction as well as the weight value. That's why we applied a new adaptive learning rate technique to mitigate this retraining issue. Next, we applied another technique called straight through estimation, where we keep the floating point weight values during training, and we apply the gradient on the floating point values instead of the quantized values. And in every epoch, we apply this gradient update on the floating point values, and then quantize before forward propagation. So this also improved the accuracy a bit. And here is a like comparison where we can see that this adaptive learning rate versus straight through estimation comparison. And here we have mixed precision as well, where we use one precision for the convolutional layers and different precision for the last fully connected layer. So these results are for ResNet 20 used for CIFAR data sets. And here you can see that for CIFAR 10, which is a relatively easier task, like both the methods have very close performance. But if you go to a bit difficult task like CIFAR 100, there we can see a clear difference in adaptive learning rate versus straight through estimation methods. And one additional change, you can see that because the last layer is very like important for classification, we also use this higher precision in the last layer with 8 bits, and that also improves accuracy quite a bit. And finally, we tested our method for ImageNet dataset, which is the most difficult one. And here we can see some clear trends. First, we see that nonlinear quantization is doing much better for difficult tasks. So if we check this right table, we see the like increasing difficulty in the datasets. First, we have CIFAR 10, then CIFAR 100, and lastly ImageNet. And we can see that in the accuracy side, compared to uniform quantization, the nonlinear quantization is doing much better for the difficult task, which is the ImageNet. But for simpler tasks, the difference is very minimal. And then we also tested the ImageNet for many different networks, like smaller compact networks with larger networks with different precision. And we compared with some literature works. One is DeepShift, which is also doing this similar power of 2 quantization. And then there's additive power of 2 quantization, that is another work which not only uses this power of 2 weights, but it also uses a combination of power of 2 weights. That means for each weight, it can use multiple power of 2 combinations. Okay, so now comes the main part of our work, which is the hardware considerations. Like in previous part where we devised or explored the algorithm and demonstrated that accuracy can be on par with the baseline models. And now we are trying to figure out how we can benefit from this method in the hardware. So first we try to apply these techniques in FPGA. And in this first table, we tried to compare the different type of MAC operations. The first one where we design a 8x8 MAC, which we are assuming as our standard baseline for comparison. And then we also use 4x8. In all cases, we are assuming our activation will have 8-bit quantization. And then finally, we compare with additive powers of 2 and our powers of 2 quantization. And we can see that the complexity is almost like half. This is lookup tables and the number of flip-flops. So the total resource required for powers of 2 is like less than half of the uniform case. Finally, we come to the memory part as well. And here something important to note that no matter how much we apply techniques in the algorithm, we need to also make sure that on hardware it has to be supported. The current off-the-shelf hardwares mostly support 8-bit compute and 8-bit compression. In that case, no matter how many bits we reduce in the algorithm, we cannot utilize that on the hardware. So some recent hardware compilers, however, are supporting additional compression technique. One of those is this ARM Ethos U Vela compiler, which is focusing on mobile hardware accelerators from ARM, and they allow compression based on sparsity and lower precision. Even though if the hardware is only supporting 8 bits, they can decompress the weights on the fly. And using that compiler, we try to measure how much compression we can get from our low precision quantization. Note that this compiler do not have the notion of nonlinear quantization. It has some built-in compression algorithms, but it does not account for nonlinearity in the quantization. So here we see that in our baseline with int8 quantization, we have like slight weight compression compared to having all values, and this is coming from some pruning based on the 0 values in the weights. Then if we apply uniform quantization, we see that there is a significant amount of zeros, like 41% of the weight becomes zeros, and that I showed in the initial slides that we lose a lot of information around the 0 if we apply a very low precision quantization for uniform quantization. And we see that impact in the weight compression, that we have almost 2x compression, and that all coming mostly from the number of zeros. However, we see that there is a good amount of accuracy degradation compared to the baseline. And then we apply our power of 2 quantization, and here you can see the first one without any pruning. We have all 4-bit nonlinear quantization or logarithmic quantization, and we get 2x compression without any like significant accuracy degradation. And we can additionally apply some pruning as well. So this goes on the memory compression side, that without making any hardware change, we can get almost 2x memory compression. So if a model is very large, we might be able to still fit that on the hardware. On the other hand, if we want to save memory leakage, we can reduce the memory size with this method without changing anything on the hardware or compute side. Okay, so now since we are using this power of 2, we should also get some benefits on the compute as well. But these traditional computes are mostly optimized for 8 by 8 multiplication operation. So we tried to design a very simple shift and add based compute unit instead of multiplication and add based compute unit. And here we are comparing with standard 8 by 8 MAC units for area and compute power. So we designed this MAC and shift and add units using RTL level design, and then we synthesized for very like advanced like 5 nanometer technology nodes. And here we can see that compared to our baseline with this 4 by 8 power of 2 hardware unit, we get almost 6x power reduction and 2x area reduction. And even if we just compare with uniform 4 by 8, still we get almost 2x power reduction. And here again, no additional optimization is applied. It's just a standard RTL design. We believe that we can apply even more aggressive optimizations in this design. So this brings us to the point that without any significant hardware changes, this can be a drop-in replacement for our standard hardware accelerators. And one major goal for this work was to demonstrate that this can be a good direction where we can head to meet our tinyML requirements. Because current like standard hardwares are getting stuck at this point that they cannot go below this 8 by 8 standard implementation without making significant changes to both algorithm and hardware. But here we are trying to show that with minimal changes with standard use cases and hardware, we can achieve significant amount of improvement. So this brings us to the end of my talk. Thank you everyone for listening, and I'll be happy to take questions. Thank you.
Hello, I'm James Tandon with Cassia AI. I was curious, very interesting talk. For your drop-in replacement, the modeler needs to retrain from scratch each time, or can somebody just take a pre-trained model and then drop it in?
Yeah, thank you. That's a very good question. I forgot to mention. So the idea is that, again, we will use this pre-trained model. One of the major issues of very low precision quantization is that if we start from scratch, we have convergence issues because the like training may get stuck at local minima. So to avoid that issue, we'll always try to use a pre-trained model and start from that. And that also reduces the overhead of this quantization effort. So we need only like 3, 4, or 5 additional epochs to apply this quantization in our training. Yeah.
Very impressive. Thank you.
Thank you.
Hi. Very great talk. Thanks a lot. That was really very interesting. My name is Neil Tender. I'm with Black Links, part of Jacobs Engineering. And just a quick question for you. Are you aware? Are you guys looking at actual hardware platform architectures to implement this power of 2 on? I mean, I see you've simulated it, kind of modeled it with an FPGA, and you've kind of evaluated what it would look like on an ASIC. But are you aware of any existing or upcoming or hardware targets where they could actually accelerate this power of 2 algorithm?
Not that we know of. We are exploring options like, for example, there are some academic efforts where people use variable weight bit precision compute. So we are collaborating with some academic labs on that. But yeah, from industry perspective, we are not aware if anyone doing something like this. And that is something we will try to work on to see if we can push towards this direction, because it's very promising. Yeah.
Thank you.
A quick clarification question. Was I right to notice that there were some quantization levels that were missing in the trained?
Yeah.
And if so, can you explain why that would be so? I mean, I was surprised by that.
Yeah, yeah. Let me go back to that figure. Here, right? Okay, so yeah, so that is important. Yes, we are missing some levels, and still the goal is that we want to keep the shape of this distribution. Even with missing these levels, if we draw a curve here, we'll see that the distribution shape is there. So one intuition is that as long as we can keep enough information, even with missing those levels, we'll still be able to deduce necessary information. And the purpose of missing those levels is we are using this power of 2 weights. This is a constraint we have put in during training, that will only use these specific levels which are not of equal distance. Yeah.
No, I understand that, but I assume you didn't take them on purpose. This was as part of the right? I mean, those, if you look at the continuous one, those values are going to be there. And now, and it's true for the uniform. For the uniform, there are no missing ones. And I'm kind of surprised that there would be missing ones.
No, so what we do is, if weight value is between these 2 levels, we either round up to the next level or round down to the previous level. So it's not missing, it's just more tuned. And here actually this here, since most of the information is concentrated in this region, the tuning error, if we have this concentrated number of levels around 0, will be less compared to having this equal distance. Yeah, maybe we can talk offline to clarify if there is any more confusion. Yeah. Sorry.
All right. With that, let's thank our speaker again.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, Pixart, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.